So we've already seen one nice thing that comes out of this, namely that if you have two vectors and you want to find a third pointing in the third direction, then you just take the cross products. Another thing this can be used for is you can find the area of certain figures. So here you have two vectors, right? Right now I'm moving my A vector around. I can also move my B vector around. And they form what is called a parallelogram, right? This is this shaded area. So the parallelogram generated by these two vectors has the area equal to the length of the cross product. And obviously the triangle generated by A and B, so the triangle generated is just this darker shaded area. So this area is clearly just half of the original area. That's geometrically clear, right? If the parallelogram is this whole thing, then clearly the triangle has half that area. So how do you prove this? I mean, what does this has to do with cross products, one might ask. So we start out with an angle less than pi half. Then this h I have here is by the trigonometric, by normal trigonometry, is just sine theta times the length of a, right? It's just taking this and then multiplying by sine of the angle. Then you get this height h. So clearly the area of this dashed rectangle here is just baseline. How long is this? Well, clearly this has length b, right? So the area of this dashed rectangle is just the product of length of b and h. So in other words, a is equal to the length of a times the length of b times sine of theta, because this h can be rewritten in this form, right? And this number is what, as we have seen earlier, just the length of this cross product. So why is this rectangle here, why is the area of that important? Well, what you should do is you should take the triangle, the right angled triangle that you have here, right, outside of this rectangle. And then you should note that this has exactly the same shape as this white right angled triangle that we have inside here. So if we just move this bit over here, we get the rectangle. So clearly what is not inside of this rectangle from the parallelogram has area exactly what is missing down here. So the area is the same. Lastly, we have these algebraic properties that we have had whenever we introduced new things. But this time you really have to be careful, because so far we've had operations that behaved nicely in all kinds of ways. A dot b equals b dot a and so on. Here we have some nice properties, but look at the first one. This is not necessarily nice, right? You have a cross b is not equal b cross a. It's equal to minus b cross a. This is not weird, right? Because the minus here, just remember how this in which direction the cross product pointed. It pointed in such a direction that you formed something which was a right-handed triple, right? So if you interchange the roles of A and B, that more or less corresponds to changing hand, right? So you get something pointing in the opposite direction. So the second is nicer. It just says that cross products respect scalar multiplication. It doesn't matter in which order you do it. You can either scale the first, the second, or the product, and the result is the same. You can also take the cross product of a sum, and everything behaves nicely. I mean, you can multiply into the parentheses, as one sometimes says. Here's something which is a bit more. I mean, this is not something you can relate to anything else you've seen. Here you see how a product, a dot product, and a cross product behaves when they sort of interact. So the dot product with a cross product is the same as the cross product times the dot product, if you remember the order of the vectors. So here you have the A first, and then you dot it with this. Of course, you could have had the A in the end, as long as you dot things. But if you want to interchange the roles of the cross product and the dot product, you should be careful that you have B cross C here and A cross B here. And then you have, lastly, what happens if you cross a vector with a cross product. So this doesn't behave as you might have hoped. It doesn't become A cross B times A cross C, just like that. It becomes this. So you get a dot product out here of A and C, so the first and the last, times B. So this is a number, right? So this number you should use to scale B, and then you should subtract the dot product of A and B times the vector C. This one and this one, I don't expect you to remember by heart, but you should remember that these exist. You should remember that there is something that you can use if you have a cross product of a cross product or a dot product with a cross product. You should be able to look this up. Also, I don't expect you to remember the definition. This definition, because it's a complicated thing, right? It's not something you use every day.